Great, thank you so much for joining us for the session this morning on creating cooler homes and schools. My name is Lad Keith, and I'm an assistant research professor at the University of Arizona, where I study how cities are planning for heat and emerging forms of heat governance, and I'll be moderating this morning's session. As we've seen from the summer, no community is safe from increasing heat risk, both from rising average temperatures that are leading to increased chronic heat risk, as well as the increasing likelihood, duration, and intensity of extreme heat events like the Pacific Northwest heat wave that occurred in June 2021. So today's presentations will explore important aspects of preparing our communities better for this heat, including an analysis of household level heat illness, an assessment of how trees and cool roofs can help decrease indoor heat exposure, and an evaluation of how to enhance schoolyard heat resilience. We're very grateful for our collaborators and sponsors who made this day possible, listed on this slide here. So thank you to all of our event collaborators. And if you have any questions for the presenters as we go through the presentations, please do put those in the chat box, which should be listed in the right-hand corner with that question icon. And our presenters today are Mary Wright of Arizona State University, Evan Mallen of Georgia Institute of Technology, and Morgan Rogers of the University of California, Los Angeles. And again, we will have about 20 minutes for each of these presentations. Please do put those questions into the chat box, and I'll be moderating some questions and answers afterwards. And if we have time at the end, we might do a short discussion with the panelists. And with that said, I would like to turn it over to Mary Wright of Arizona State University.
Hello. Hi everyone. Yeah, my name is Mary Wright. I'll be presenting a results from our meta-analysis of social environmental factors predicting household level heat-related illness in Phoenix, Arizona. If you're unfamiliar with what a meta-analysis is, I know we are supposed to have sort of a mixed crowd here. It's just a statistical method to combine the results from multiple surveys into one sort of summary estimate, or multiple studies, and in this case we're using surveys. Of course, everyone here, I'm sure, is very aware that heat can impact the health of people in our communities. It's also important, I think, to keep in mind that heat can impact quality of life. There's lots of different ways of looking at this, but I know we have some studies that show it can decrease cognitive function, it can exacerbate mental health disorders, these sorts of things. And of course, something that's important to me in my work is that heat impacts are not equitable, and that's both from a physiological perspective. Maybe someone has pre-existing conditions like heart disease or these things that make them more susceptible to heat. And then also the social and behavioral side of things, where maybe someone may have an air conditioning, but they don't have enough money to use the air conditioning as much as they want, these sorts of things. Most studies related to heat and its impact on people tend to focus on severe health events. And this is by no way a critique that this is a great thing. Of course, it's incredibly important that we focus on these things. But in this figure here that I borrowed, we can see that the most extreme events affect the least number of people, and there's likely a large number of people that are experiencing the less severe events at the bottom of this pyramid here. And so even if people aren't necessarily ending up in the hospital, they're still having a pretty substantial quality of life impact. Additionally, most studies related to heat use aggregated data. So an example of this is this figure here of a heat vulnerability map produced by Sharon Harlan. And you can see everything is aggregated to the census block group. And so everyone who lives in that block group is assigned the same value. When we do this, there's a couple things that happen. It can be hard to measure something like adaptive capacity, which is sort of more, can be a more like individual thing that's not typically included in things like the census or other broader metrics like public health records. And then we also introduce the possibility of an ecological fallacy, where we make these inferences about relationships at the aggregate level, and those may or may not hold true at the individual level. So our study site is Phoenix, Arizona, which of course is well known for being quite hot for the entire summer. I think the high today is actually supposed to be 108 degrees. Because of this, most residences have central air conditioning. But in spite of the central air conditioning, we still have a substantial number of people that die every summer from the heat. So it's a major health concern here. Because of all this, there's been a lot of research done in Phoenix and studying Phoenix. And part of that research has included a number of residential social surveys. And this table here is a list of the social surveys that we've compiled for this meta-analysis. And each of the surveys is administered by a different municipality, like the Maricopa County Department of Public Health, or a research group, typically at ASU. Some of these I've been involved with, some of them I haven't. But you can see they were done in different years. They have different sample sizes. Each of the surveys kind of targets a different population. But they do have a few things in common. Of course, they're all in Phoenix. They're all administered to residences, so people's homes. And most importantly, they all ask whether or not people there experienced heat-related illness recently. So we've made this sort of conceptual diagram to get at the questions that are overlapping in the survey. So of course, all of them down at the bottom here, all of them have this question, self-reported heat-related illness, and to varying extents, all of them share these other questions. And we're interested in the relationship with these questions, which are potential vulnerability indicators, and how they influence self-reported heat-related illness. This figure just sort of demonstrates a conceptual way of thinking about these different questions where they are more proximate to heat-related illness. So say like direct heat exposure is going to be directly related to experiencing heat-related illness, adverse heat health outcome. Whereas something like sociodemographics, income and stuff, there's a few steps in between before you get to an adverse heat health outcome. And so we're taking all of these various questions and essentially synthesizing them, their relationship with self-reported heat-related illness into one sort of summary estimate using meta-analysis. I can turn this arrow off. There we go. So there's two steps to this. The first step is to calculate these effect sizes for each individual survey. And so there's a few steps within that as well. So the first thing we do is identify these shared survey questions, as we've done, convert the survey questions as needed to binary responses. So depending on the survey, some of the questions have different response scales where you might have 3 or 4 options, and some of the surveys only have, a yes/no option. And so just to make it, to streamline all of this, we converted them to binary responses. We also, in our model, control for household size, where household is the level of unit of analysis. And of course, this is important because if we're looking at number of, or the more people that are in a household, the more likely they are to have somebody in the household experience heat-related illness. So we want to control for that. And lastly, we actually run the model. So we use logistic regression to calculate the odds of experiencing heat-related illness given that some survey question is true. So we'd be saying the odds of experiencing related illness given that someone responds that they are too hot in their home. Okay, so the second step is to actually run the meta-analysis. So we have all these individual effect sizes for each individual survey, and we can use this. This plot here is a sort of visualization of the results of a meta-analysis. So I'm giving you a little bit of a sneak peek of what the results are actually going to look like. And you can see each of these here are the individual effect sizes for each survey. We have our 95% confidence intervals. And when we're looking at odds ratios, we want to be thinking about it in terms of odds. So we really want something either greater than 1 or less than 1 to be seeing an effect. So greater than 1 is going to indicate a positive effect. So this 2 here, you would read this as people are twice as likely to experience heat-related illness if they respond that they are too hot in their home. And so then we take all of these together, we synthesize them, and then we generate this summary estimate. And on the next few slides, if all you really pay attention to is the summary estimate, that'll be fine. That's what you need to be paying attention to. That's the actual result of the meta-analysis. So we use a random effects model in the meta-analysis. So that way we can minimize both the within study or survey variance, and that's sort of the natural variance you're going to see in any individual study. But then we're also minimizing the between study variance. So that's going to be variance due to just sort of natural differences in just talking to different people that you might see, but also differences that are due to having different response scales. Maybe the question that we're looking at is worded slightly differently. These sorts of things can be accounted for. And then part of looking at that is also looking at the heterogeneity of these effect sizes. So we want the effect sizes to be as homogeneous as possible to have a good meta-analysis result. And we can quantify that with various statistics, and I'm happy to get into the nitty-gritty of these if anyone is interested, but essentially all of the results I present here have adequate measures of homogeneity between the effect sizes. So we can sort of trust that this is a good result, that we're seeing consistency between surveys. All right. So now this is the same figure we were looking at before. Are you or members of your household ever too hot in your home? We see the summary estimate here, indicating that people that are too hot in their home are twice as likely to experiencing heat-related illness, according to this meta-analysis. I think this is a really important point, especially obviously for this session, looking at cooler homes. It's not necessarily something we think about a lot. We consider that if people have air conditioning, they're good to go. But that is not necessarily the case. And considering that people spend so much of their time at home, I think the American Time Use Survey says something like 70% of time people spend at home. Being too hot in your home is potentially a pretty considerable contribution to your overall heat exposure. And so I have this figure here again on the side indicating that we're in the heat exposure category and most proximate to heat health outcomes. All right, so our next question is, do you or does any member of your household work outdoors? And again, we see positive results here. People are twice as likely to experience heat-related illness if they work outdoors. This is probably not too surprising. Obviously, working outdoors is going to contribute to overall exposure, and very possibly working outdoors is where they experienced heat-related illness. Okay, so our next question is, do you and or your household use central air conditioning to cool your home? There is a definite protective effect from doing so, although our statistical significance is really getting quite close to 1 here, which would indicate a null effect, if that were true. However, not unexpected to see this result, and perhaps more significant because most people do report that they have central air conditioning. So this is indicating that those that don't almost certainly do experience heat-related illness. Oh, there we go. Sorry, getting used to the interface here still. Okay. So the next question asks about window air conditioning. Now this one is interesting because people that use window air conditioning in Phoenix are almost twice as likely to experience heat-related illness again. And you would think that window air conditioning would be protective, but I think that in Phoenix, it's simply not enough. I know from experience, like lived experience, that just having a window air conditioning is not going to do the trick to keep you as cool as you would want to be. So interesting finding here in Phoenix. And then we asked about restricting air conditioning due to concerns about cost. So another important point here about people that restrict their air conditioning use because they're concerned about how much it costs are more than twice as likely to experience heat-related illness. And this is I keep like drumming it home, like this is the important point that like somewhere like Phoenix, where it's just always hot, just having air conditioning alone is not necessarily enough to keep you as cool as you want to be to protect you. And moving on to our social isolation category, we have one lone question in the social isolation category, and while it is not statistically significant here, we cross the boundary. It does tend towards being somewhat protective to live alone, and this is, again, remember, we're controlling for household size, so it's an interesting finding. I think it runs contradictory to a lot of what we see in the literature, that living alone is more risky. We could definitely unpack this some more, and happy to do so in Q&A session. All right. Our next question is about home ownership, and we can see here that home ownership is quite protective. People are 40% less likely to experiencing heat-related illness if they own their home. There's a couple ways you could look at this, and I'm definitely open to other ideas if people have some thoughts in the Q&A, but I'm imagining people that own their home probably are at a little bit higher socioeconomic status in general, and then people that own their home also have more control over their home, where they can weatherize it, they can improve their air conditioning unit, these sorts of things. Our next question is about household income. Here we're asking if their household income is less than $40,000. And we see that people that make that lower income threshold are about 50% more likely to experience heat-related illness. This is probably in line with most literature that we've seen. However, the results aren't, this is the one time I'll bring it up. Our values here for our heterogeneity of our effect sizes are not the best. They're probably, in fact, they're probably the worst of this set of results I'm showing you. So there is some like push and pull, like different surveys are indicating different things about the importance of income in heat-related illness. Our next question is identifying as Hispanic, and we see here that there is a little bit of an increased risk of experiencing heat illness. for Hispanic people. And of course, we're not, saying there's anything like intrinsic that would make Hispanic people more likely to experiencing heat illness. There's, the long history of social inequalities and these sorts of things that would make Hispanic peoples maybe a little bit more at risk of experiencing the negative impacts of heat. All right. Next up is education. We're looking at whether people have a bachelor's degree, and we see that as somewhat protective. Exactly what we would expect. People with a little higher education probably have a little more access to resources and maybe a little more knowledge of heat and how to handle it. And our last question is, are you over the age of 64? And this is an interesting one because we see that being over the age of 64 is actually very protective in these surveys and our meta-analysis. And granted, there's only a handful of surveys we were able to use for this question, but it does run contrary to what we might think in general. And my thought is that people over the age of 64 probably aren't spending nearly as much time outdoors, but then of course, if they are exposed to heat, they are physiologically much more at risk of having negative impacts. All right. So in conclusion, I hope I've really drummed home the importance of the indoor environment and how if we're really serious about addressing the impacts of heat, we have to be thinking about indoors as well as outdoors. Of course, home ownership may play an important role in controlling the indoor environment. And I would say, apart from the questions about living alone and being over the age of 64, in general, these measures that we saw in the meta-analysis matched sort of anticipated relationships. And then, of course, limitations, we always want more data. Like, it'd be amazing if I had 40 more surveys to pull from. But in terms of meta-analyses, having 7 surveys is actually, quite good and maybe better than the majority of meta-analyses. And of course, I have to acknowledge my grant funding from CAP-LTR, our 3HEAT National Science Foundation grant. And thank you very much to the people that have administered these surveys, or the Maricopa County Department of Public Health, City of Tempe, the ASU Knowledge Exchange for Resilience. And I completely spaced when I was making this, but of course I have to thank the ASU Urban Climate Research Center as well. There are my references. And thank you so much. I'm happy to take any questions.
Great, thank you so much, Mary. We have one question that's, how can health conditions such as chronic diseases and obesity be factored into your analysis in the future?
The trouble with this analysis is it is limited to the questions that were asked in the surveys. So if future surveys ask these questions, we can factor it in. I think I have looked at that. Only one of the surveys asks about people's weight and height. So you could get it like BMI or something like this. So you can't really run a meta-analysis with that alone.
Yeah, it seems like that's a future recommendation for folks that are administering these surveys, right?
Yeah.
We have a similar question that I think you'll have the same answer to, but also thinking about household unit typology, inequality of upkeep, weatherization. So same answer for that one, right, Mary?
Yeah, absolutely. I think, it's possible we could look at the age of the house. It is possible to get at that if we know the location of the households that answered each individual, the responses. We could maybe look at we have tax assessor or assessor data that we can see the age of the house, which might tell us something, but hard to get at that one.
Okay. And for participants participants who have joined us, please do use that questions and answers box for this presentation and for the following ones. Mary, one other question is, what would be your recommendations to decision makers based on what you found from this meta-analysis? Are there any takeaways that are for those in practice that they could use this information for?
Yeah, absolutely. And I hope I have. I'm gonna say it again. Like the importance of looking at the indoor environment and checking in on the actual temperature inside people's homes. And when people say that they're too hot in their home, they probably are really too hot in their home and need some help. So.
Okay. And one final question. Do you think there's a protective factor, kind of speculating, do you think there's a protective factor for those older adults living in Phoenix from the neighborhood effect of perhaps living in an adult community?
That is possible. We didn't necessarily, as far as I know, the surveys didn't target adult communities specifically. But I suppose that is possible.
Okay, great. Thank you so much, Mary.
Yeah, thank
Now
you.
I'd like to bring Evan Mallen on stage. So if we could have that. Give Evan a second to load his camera and mic up. All right, so I'll turn it over now to Evan Mallen of Georgia Tech for his presentation. And again, we'll run about 20 minutes and we'll do questions and answers after. So please continue to put those questions in the chat box. Evan?
All right, thank you very much. So my name is Evan Mallen, and we're going to be talking today about the cooling potential of tree canopy and cool roofing on indoor heat exposure in concurrent heat wave and blackout events. So let me get this. There we go. Okay. So there we go. So this is a broad effort from a handful of researchers from Arizona State University, of which Mary was one, and Georgia Tech. So thank you to everyone who participated and contributed to this research. So heat, even now, kills more people than any other weather-related disaster combined. And this is something that is expected to get significantly worse in a warming climate. Heat waves are increasing in their frequency, duration, intensity, and timing. That is how early they are coming in the year. So this is a trend that we've been observing for a very long time. And of course, heat is further exacerbated as we begin to look at the urban heat island. And we're going to see it get even worse as we start looking into interior temperatures, not just exterior. We also have a trend of rising power outages. In fact, over the study period that you see here, we've seen power outages increase by about 60%. We're seeing a lot of power outages nowadays for a variety of reasons, not just stress on the grid from increasing power usage during things like heat waves, but we most recently have been seeing power outages resulting from events like wildfires and hurricanes. And Hurricane Ida just recently knocked power out for about 1.2 million customers. So we're seeing this quite frequently, concurrently with other weather-related disasters. We also know that mortality can increase rather sharply as temperatures increase. And this is different for northern versus southern cities. That is reflective of our what we call physiological acclimatization. So those in southern cities who are more used to the heat will not be quite as impacted by it. But northern cities, you can see here, I seem to have lost my cursor ability. Oh, there we go. Okay. So we can see here, the northern cities increase that mortality risk quite sharply as temperature increases. So I want you to keep these kinds of relationships in mind as we start to look at just how extreme this heat exposure can be inside our own homes when we turn the power off. So this study has 3 different research questions. The first being, how do building interior heat exposures change during a concurrent heat wave and blackout event for different residential building types? Second is, how effective are cool roofing and tree canopy in reducing building interior heat exposures? And third, how do building interior temperatures vary with the spatial intensity of the urban heat island, that kind of heterogeneity that we get across a city due to the urban heat island? So our study population is in 3 different cities in very different climates. So we have Phoenix, Atlanta, and Detroit, representing 3 very different climates. So let's dig into research question number 1. So this uses a coupled modeling approach. So we are modeling exterior temperatures using the Weather Research and Forecasting Model, or WRF, as it's known. This is where there is a large body of research. We, for a very long time, have been analyzing exterior thermal exposure due to the urban heat island. So these kinds of differences that you get in, say, hotspots across a city, due to built up temperatures or high temperature materials like impervious materials, blacktop, that kind of material soaking up the sun and elevating temperatures. But where we're headed with this is we want to get as close as we can to the actual lived experience of people in these cities, and we are not outside all the time. And so we've coupled our WRF model with a model that is based on Energy Plus to model interior temperatures. And so when the power is on, we have very cool indoor temperatures. And so to get at research question number 1, how do these heat exposures change during a heat wave and blackout? We turn off the power. So we have a variety of temperatures that come from WRF due to the urban heat island. So that is, you can see we have kind of our hot spots. This is Phoenix, and then areas of the city that are much, much cooler. And then we have a modeled heat wave. This is a historic heat wave in the last 20 years, modeled for each of our 3 cities. And this, of course, is with the power on. And then we turn the power off. And so we expect those interior temperatures to rise during this kind of compound event. We have 3 different building prototypes that we use in this study. We have 1-story single-family housing. This is kind of more elongated to fit in all the rooms you need in a home. We have a 2-story single-family house that's a little bit more compact, but of course 2 different stories. And then we have an apartment complex. This is a relatively low rise at only 3 floors, but what we're modeling here is actually the 3rd floor southeast facing unit. So you're going to get more of that kind of solar insolation, more of that coming into your home through the windows. And then looking at number 2. So this is where we start to analyze the cooling potential of cool roof and tree canopy. So we have 3 different scenarios that we use. We have no adaptation, that is using common building materials. And this is up to the 2006 building codes for each city. So we actually do have the buildings reflect the type of housing stock that is really on the ground in each of our 3 cities. And of course, we have cool roof, where we're going to be reflecting most of that incoming solar radiation, ideally reducing those interior temperatures. And then we have tree canopy, where we actually plant trees to cover about half of all roadways in the city. But we also have trees planted around the homes. So you get both the ambient cooling that comes from increased tree canopy, but then also that direct shading. So that's just illustrated here. So no adaptation, of course, conventional roofing. We leave the tree coverage where it is, as observed in these 3 cities. The cool roof is an assumed 100% conversion. So every building has a cool roof. This, of course, affects not only the interior temperature, but there's a feedback loop here where it's also going to impact the exterior temperature. So that's modeled, that's captured in our WRF model. And then tree canopy, 50% canopy coverage over road surfaces, and of course with that direct shading. And that looks a little something like this. So we do use some native species, some very common species that you might find in all 3 cities. And of course, that's going to look very different depending on where you are, based on the climate that you are in. So Atlanta has a red dogwood. It's about a 15-meter tall tree versus, say, Phoenix, Palo Verde, it's only about a 4-meter tree. You don't get a lot of big leafy trees in a desert. So those are going to be very different types of trees. And so that's also going to be important for us to keep in mind as we see some of these results. And then for our 3rd research question, how do building interior temperatures vary with the spatial intensity of the urban heat island? We apply these across the heterogeneity of the urban heat island that we see in these 3 cities. And so that, just to illustrate it, this is Phoenix. So we look at warmer versus cooler areas of the city for these 3 different building prototypes. And we want to actually put them where there are people. And so even though you saw an enormous heterogeneity coming from the urban heat island in that last map that I showed, where we actually have the most people, where we might find these building prototypes in Phoenix, we have a UHI intensity of about 4.5 degrees Fahrenheit. And you can see where we've put those. So these are the warmer areas of the city where we're going to put those hot cells. And then these are the cooler areas up here in the north. All right, so let's talk about some results. So for research question number 1, what happens when we turn the power off? So what you see here in blue is the interior temperature. These are daily maximum temperatures over the heat wave. So this is about as bad as it might get. But of course, this is also on average across all 5 days of our modeled heat wave. So in Atlanta, you can see that things can heat up quite a bit. They get about 17 degrees warmer in a single family home when you turn that power off. Now, I'm glad that Mary before me talked about energy poverty, this kind of environmental justice issue that is having access to air conditioning and being able to afford to use it. So this may be during a blackout, but we also have homes in all 3 cities right now who just cannot afford to use the air conditioning that they may or may not already have. And so this is pretty routine for them. When we have really warm temperatures, they may be pretty routinely exposed to 95-degree maximum every day. So let's turn now to Detroit. Detroit actually looks very similar. We get about a 17-degree increase for that single family home when you turn that power off. But when we turn to Phoenix, this is where it gets quite extreme. So you can see here the housing stock in Phoenix is under normal conditions very good at maintaining its target temperature. So we have the assumption that you're going to set your air conditioning at about 75 degrees when the power is on. As soon as that power gets knocked out, you might gain about 40 degrees Fahrenheit, going up to about 115 inside your home. And that is a major difference. Now think of those relative risk of mortality curves that I showed earlier. This is very sharply going up that curve. And this is where you're going to see major health impacts that come from such a quick transition up 40 degrees in your own home. So to take a little bit of a deeper dive into what that looks like, these are the hourly results for Phoenix with all 3 of our building prototypes. And what you can see here is ambient is in black. So you can see, of course, that goes up and down as it warms up and cools off over the day. But our 1-story single family homes shoot way above that. Your home is a little oven. It's going to get higher than that ambient temperature. You're going to heat up quite a bit. And then when you get to the overnight minimum, you are going to store some of that heat. And so you're not actually getting as cool as outdoors overnight. And we see here from 2-story and from the apartment buildings that they do not reach that same ambient, but they also, again, maintain that heat. This is because these buildings have more thermal inertia, as we call it. And so this is something that's going to be very important to see when we look into some of our next results. So how do we cool off? If we have cool roof, if we have trees, what does this look like for our 3 cities? And so what we found for Atlanta is that for 1-story homes, we actually get the greatest cooling benefit from cool roof. You get about 1.7 degrees Fahrenheit cooler. But for 2-story, where you have these little bit more compact homes, but they do have that extra story, we get a huge benefit from tree canopy. That tree shading is actually going to cool you off by 5.5 degrees Fahrenheit. So this actually speaks to the differences that we might see in what kind of cooling strategy we're going to use that will be most effective in a city. And it depends both on your housing type and where you are, as we see very shortly as we start to dig into some of our other cities. So in Detroit, we actually see some of the greatest benefits coming in the single family, the 1-story single family, and we see the greatest benefit coming from tree canopy. So for those trees in that city, for that type of housing, we see that you get about 8.5 degrees cooling if you have adequate tree canopy in Detroit. And then for Phoenix, we actually see that cool roofing is the most effective for that single family home. You get about 4.5 degrees Fahrenheit cooling and only 2 degrees of cooling. Now remember, This is a very different city. It's a very different climate. You have different housing stock. And of course, the trees that you're using to shade these homes are very different for what we're actually able to plant and maintain in these cities. So you're going to have a very different response depending on where you are, what type of housing you have, and what kind of trees you're actually able to use. So now let's look into the urban heat island impact. So what we see here is our warmest areas of the city for the same kind of housing stock here, our three housing prototypes, minus the average for the cooler areas of the city. So this shows what kind of difference you might get depending on where you live in the city. What we see here is that Atlanta doesn't make that much of a difference. Even though we have a fairly extreme urban heat island, our housing interior temperatures, that's not going to get very different depending on where you live. So this may imply a very different kind of policy response. In Detroit, however, we have a very big difference. And so where you live in the city, that might start to change how we think about ways that we are going to be trying to mitigate those temperatures. So you might have a very different neighborhood by neighborhood type of response in this. But this brings up an interesting new concept that we've kind of coined through this research. It's what we call the UHI penalty. That is the difference in interior temperatures between the warmest and coolest areas of the city within housing type. That was on the last slide. And what we call the housing penalty, the difference in interior temperatures between the warmest and coolest building type for each city. And what we saw is generally the warmer building types are the one-story single family, and the coolest building types are those low-rise multifamily. What we see here is that the housing penalty is significantly larger in all three cities than the UHI penalty. So this really implies that we should be thinking about our urban heat island response differently than we have been for the past several decades, which is look out for your hotspots and do what we can to reduce those exterior temperatures. Now that we're starting to move into a modeling regime that gets more towards our lived experience of individuals and where they live and where they actually spend a lot of time, we should probably be looking more at what type of housing they live in and basing our response on that. And so this may have some pretty big implications for how we model our climate adaptation policy. So the conclusions from this study, concurrent heat wave and power outage can substantially impact indoor heat exposure up to 40 degrees Fahrenheit in Phoenix. And that's just for the one-story single family housing units. Heat mitigation strategy effectiveness varies widely by city and housing type. It really depends on what type of housing you're living in and what you're actually able to plant and what your housing stock looks like. And the third major conclusion is that the housing penalty exceeds the UHI penalty in all three cities. So we should be thinking a little bit differently about what we do in these three cities, or really any city. So from this, I have a few recommendations for policy. And what we see is that we should be preparing now. We are already seeing these kinds of concurrent events where a heat wave and a power outage can come at the same time for a variety of reasons, but we do see those trends increasing and not in a good way. And so we should be preparing now. We should be using both passive and active cooling strategies. So that's passive light cool roofing and tree canopy, but also active in terms of getting more of a personal adaptation type of response, opening those cooling centers, using phone trees, checking on elderly residents, things like that. Number two, housing matters. We saw from this study that the type of housing you live in makes a huge difference on the type of thermal exposure that you actually have during a concurrent heat wave and power outage, as we modeled in this study. So we could be identifying vulnerable populations by housing type for a very effective type of intervention, more so than our exterior hotspot type analysis. Three is that there's no one-size-fits-all solution. For a very long time, and I've been doing this research for quite a while now, we say plant trees everywhere, put those cool roofs everywhere. But what we're finding from this research is that it really depends on where you are. It depends on your climate, depends on your housing. So there's not really a one-size-fits-all type solution. We should be looking more into what might actually be most effective for your local context. And then four, of course, look beyond those hotspots. We should be implementing strategies in warm and cool areas of the city, not just in the hotspots, as we've been discussing for the last several decades now. So where are we headed with this research? This is only 3 building prototypes of many that we have already run. And so next up is to start exploring more of these types of building prototypes so that we can get even closer to the actual lived experience of residents in these 3 cities. We have already published on doing a parcel level risk analysis, but we want to be digging more into actually applying these parcel by parcel to really find exactly where we might want to be intervening, and to have more of a kind of scalable approach that we can have to more cities. And then we want to go that next level down. So we've gone from exterior to interior to now we want to be moving more towards individually experienced temperature IET using synthetic population data sets. So maybe next year I can tell you a little bit more about that. So that's all I have for now, but thank you everybody. I look forward to your questions.
Great, thank you so much, Evan. We have one clarifying question, and it was, did you use the 2006 building code?
Yes.
Okay.
Yeah, so for the results that we showed here is the 2006 building code, and then we actually do have modeled 2012 building codes, but just to keep them a little bit more consistent across the results that I shared today, they all use 2006.
Okay. We have a question about the context of different heat mitigation strategies that you already touched on a little bit, but kind of a concern over the appropriateness of increasing tree canopy in locations that may have the wildland-urban interface, the WUI kind of risk with all of the wildfires in the West right now. So can you speak to that a little bit more about the context of these different strategies in different locations?
Oh, absolutely. So the context of what we're choosing to use to mitigate these temperatures should not just be what seems to be the most effective, but we really do need to be responsive to your local context in terms of how can we encourage planting more trees right next to homes when that may be kindling for a wildfire. And I know that there's a lot of wildfire regulations nowadays that say you need to be absolutely clearing as much as possible away from a certain zone around your home such that you don't have kind of a pathway for that wildfire to just reach its way right to your home. And so that is what I mean broadly by the context is we need this kind of broad environmental context, this holistic picture of what it means to be incorporating these kinds of strategies. Now, fortunately, these kinds of hotter, drier climates where we are worried more about wildfires, we've seen from the Phoenix example that cool roofing tends to be the most appropriate in terms of what actually gives you the most bang for your buck. And this is something that I would also encourage as an immediate relief. So you can today or tomorrow go out and paint your roof white, but it's going to take you about 20 years to grow that overstory canopy if you plant those trees right next to your home. So that is a great question because we absolutely do need to be taking that holistic view to the context.
Great, thank you. We have another question about the ownership arrangements of these different housing types and if they perhaps might favor one strategy such as cool roofs over different tree planting retrofits. And kind of if you could speak to the ownership arrangement of these housing unit types.
Absolutely. So I'm glad that Mary touched on this in the last presentation because renters have an extraordinarily difficult time because landlords tend not to want to put as much money into those units. And we have seen over and over here in Atlanta that nobody wants to plant trees either, even when they are offered to them for free from groups like Trees Atlanta, because they don't want to deal with the litter. And so this is where I think that some of our more active measures may be more appropriate, actually, to try and offer relief through something like cooling centers or phone trees or distributing portable air conditioners to the units that really need it who may not be able to afford to use it, many of whom are renters. And so that's where we just need to be thinking of alternative strategies, both active and passive. But we've also seen very successful financial benefits in places like Louisville, Kentucky. So they've actually incorporated a few policies to actually help fund tree planting and cool roofing. So even if you are a renter or a landlord and you just know that, hey, it's about time for me to put in that big chunk of change to get a new roof on my house, well, they'll actually help you pay for it if you use cool materials in your roof. So these kinds of policies are also something that we could be employing across these cities to really see a great benefit for both owner and renter alike.
Great. We have another question asking if you could elaborate on why multifamily homes didn't see as great of a benefit in the first two cities from cool roofs or trees.
Yeah, so a lot of where we've landed on this is related to the surface area to volume ratio of these buildings. So they just have such a higher thermal inertia to them. So they take a little bit longer, the multifamily, I mean, but also two-story single family. They take longer to warm up, and then they also take longer to cool down. The other thing that is impacting these is that the multifamily was on the 3rd floor. And so particularly where you have very short trees, like in Phoenix, that's just not reaching them. And so in our models, we're not picking up on the same kind of direct shading that you would over much shorter housing stock. And so those two together really mean that the multifamily is going to be almost protective, in fact, quite protective, which is contrary to our prior belief that multifamily could actually be a vulnerability, particularly in the higher floors, because we know heat rises. But what we're seeing here is actually the building dynamics actually keep those maximum temperatures lower. But of course, they also elevate the minimum, which is very important for a public health standpoint, in that sustained minimum temperature can be very dangerous to our public health as well.
Great. And I'll wrap up with a two-part question. So the first part is, how do you think the model results may have been different if you used actual ambient air temperatures versus land surface temperature maps that I'm guessing is probably what you drive the urban heat island severity from, correct?
No. So the WRF model actually does model 2-meter ambient air temperatures. So that is what we're using. So that is why we use WRF. Is so that we can get an actual air temperature model.
Interesting.
Comprehensive across the entire city. So it was run for this study at a 1 kilometer resolution. And
I guess the second part that one of the questioners also asked is, does that model take into account humidity levels too? And humidity levels is something that can be impacted by trees too, of course. So
it absolutely does. And so that is something that we have published on. So the parcel level analysis that we have published on does use heat index. So we use both that temperature and relative humidity together to calculate a heat index. I considered using that for this presentation, but it starts to get, it gets a little tough for Phoenix because humidity is just so low that it really draws down that heat index. So I just opted to show air temperature for this particular one, but we do have humidity, and we actually can present that as well. Okay. Maybe for next year.
Great. Well, thank you so much, Evan. And if we could bring up Morgan, need to move along with the rest of the presentations. And Evan, I believe there's still a few unanswered questions in the chat. So if you have an opportunity, you might be able to go into the chat and directly answer those. And with that, I would like to introduce Morgan Rogers from University of California, Los Angeles, who is going to be wrapping up our panel today, speaking about enhancing schoolyard resilience to extreme heat. Morgan?
Thanks. Yes. My name is Morgan, and I'm a PhD student in urban planning at UCLA. I'm also a graduate student researcher at the Luskin Center of Innovation. And today I'm going to be presenting some work on behalf of the rest of the team, Dr. Kelly Turner, Dr. Ariana Medell, John O'Con, Florence Schneider, Yusha Zhang, and Meg Seeley. We're a big team. The work that I'm presenting today is actually part of a larger project that pursues actionable science and the co-production of urban heat profiles, as well as cooling mitigation scenario development in 5 communities in California, in partnership with local stakeholders. Today, I'm focusing on the work that we're doing to evaluate and enhance schoolyard heat resilience in schools across Southern California. And in particular, I'm going to focus on preliminary data results from public schools in the Watts neighborhood of Los Angeles, California. So as I mentioned, this, we start off with a larger project where we were comparing pedestrian heat loading, thermal exposure by land use, modeling plan and future cooling interventions in 5 communities. And we were doing a baseline analysis of land surface temperature. And we were looking at the map of Watts and noticed this big dark red spot. You know, it's one of the hottest points in the neighborhood. And we're like, gosh, what is that? And so we looked at Google Earth imagery and realized it was Markham Middle School. It's, you know, actually their sports field and, you know, schoolyard, and the sports field has AstroTurf. And the surface temperature was 57 degrees Celsius. That's, you know, 135 degrees Fahrenheit. So the AstroTurf and the schoolyard were the same temperature as the surrounding asphalt of the roadways. In other words, it's just really hot. And so that got us thinking, gosh, I wonder if, you know, the other schools are this hot. And so we started looking at all the other schools throughout the neighborhood, and we also discovered that, you know, they're dangerously hot. And so that's kind of what spurred this project to kind of look more into enhancing heat resilience of schools, and particularly schoolyards. And one of the, you know, main reasons is, you know, children are extremely vulnerable to heat stress, and you know, kids need to play outside for you know, physical, mental well-being. You know, we have recess time, so they're going to be outside. And there's a lot of pros to this physical activity, but if it's that hot out, as Marian mentioned earlier, you know, heat exhaustion actually impairs cognitive function. So, and you see this during particularly hot days, that this can impact test scores. You know, on the physical side, it can cause, you know, heat exhaustion, muscle cramps, and really extreme cases, heat stroke. You know, one study that was done out of Canada of a bunch of schoolyards, 275 schoolyards, found that, you know, the surface temperatures were hotter than the surrounding streets on average. So this is a big issue. The other reason why we wanted to pursue this topic is that there just isn't a lot of data out there on thermal conditions at the micro scale level, especially in schools. You know, there's a lot of urban climate data, but it's more at the local, like hundreds and thousands of meters, and regional scales, like looking at cities, not at this micro scale or human scale. And it's not looking at mean radiant temperature as an important heat indicator. A useful proxy measure for thermal conditions at the human scale is mean radiant temperature. And what that does is it measures the net thermal exchange between an object like the human body and the objects surrounding it. Why is this important? Thermal environments are scale dependent, and they're influenced by the thermal properties of surface and building materials, urban design, and weather conditions. So this heat measurement isn't being used as an indicator in a lot of heat assessments. And that's due in part because it's difficult to measure. But we need to, because it's critical to understanding how design interventions improve thermal comfort, not only for pedestrians, you know, walking around the neighborhood, but kids that play in our schoolyards. Lastly, the reason why we wanted to pursue this is that there's active efforts being made by various government agencies and NGOs to try to address rising urban heat in neighborhoods and schools. And so we want to provide actionable science to decision makers to inform cooling interventions. So this is the study area that we're investigating. As I mentioned before, we're looking at multiple cities. So the California Strategic Growth Council has funded several transformative climate communities, one of them being Watts, with the idea of implementing design interventions that reduce greenhouse gas emissions and provide environmental co-benefits, like mitigating the impact of rising urban heat on vulnerable populations. And as part of this program, UCLA is assessing thermal comfort of these interventions with community stakeholders in order to improve the design and implementation of projects. What this map shows, I'm focusing here on the schools. These are the 12 public schools in Watts. The schools that are in the green boxes are ones that are receiving greening projects to mitigate the heat. And then this blue box right here is Grape Street Elementary. I highlight this box because we have some preliminary microclimate modeling data that I'm going to share in just a little bit. So I'm going to go over our methods. This project combines remote sensing and on-the-ground observations of multiple temperature indicators. So we do look at air temperature, we look at land surface temperature, and then we look at mean radiant temperature. And we did this with community engagement. So from beginning to end, we were working with community stakeholders to gather heat data, inform evaluations of design interventions, and also to provide training to enable future heat self-monitoring. To measure indicators of urban microclimate, so we first used the multispectral satellite imagery to assess vegetation, surface reflectivity, also known as albedo, land cover type, land surface temperature. And then we went out in the community with residents and we placed eye buttons throughout Watts to get local air temperature and humidity readings. And then finally, we're evaluating thermal comfort pre and post intervention through microclimate modeling, as well as assessing plausible future interventions. To do this, we're using a three-dimensional computational fluid dynamics model. It's called MVMET. And what it does is it simulates surface, plant, and air interactions at a high resolution. And then we validate this model with local weather observations. So now we're going to get into some results here. This is from a remote sensing analysis of land cover and vegetation health. We use the National Agricultural Imagery Program. So that has a 1 meter resolution. Those blue triangles are schools, just to show you the locations. Just like kind of a quick cut of the data, about 62% of Watts is impervious materials, like asphalt, concrete, and buildings. 14% is dry vegetation or barren soil. And then about 12% is green vegetation, which isn't super high, but it's actually the highest among the neighborhoods that we're looking at. Interestingly, it has the highest green vegetation, but also the highest cover of impervious and building materials. This is looking at albedo or reflectivity and land surface temperature. Again, those blue triangles indicate the school locations. The lighter colors on the land surface temperature indicate high temperatures of up to 60 degrees Celsius. That's about 140 degrees Fahrenheit. Again, you'll notice here, that's Markham Middle School right there, and you'll notice that the schools are in some of the lighter areas. The albedo, the low albedo is indicated by dark shades, which is most of Watts, and that kind of makes sense since over 60% of Watts is impervious materials and buildings, and all those have low albedo. This is getting into our results from our eye button readings. So we had 15 eye buttons and a humidity reader installed throughout Watts. And what these did is they took readings every 15 minutes for the month of September. And what you'll see in this chart is it's the cumulative readings for that whole month. And you can see that the temperatures often exceeded 35 degrees Celsius, which is around 95 degrees Fahrenheit. And then if you pair these high temperatures with the average humidity levels, which was around 60% in Watts, it can be quite dangerous to kids outside. And just to kind of give you context, we use the National Weather Service Heat Risk Index. What it does is it measures how hot it really feels by combining that air temperature with relative humidity. And they use it to inform, to actually send out official heat watches and warnings and advisories. So when we combine that temperature with the humidity, we see that Watts falls within this orange region. And this means that that's labeled a danger zone. And that means that kids could potentially experience muscle cramps, heat exhaustion, and even sunstroke when playing outside. So the bad news is, the temperatures, overall temperatures are continuing to rise. As others have mentioned, extreme heat events, they're becoming more frequent, extreme, and longer. But the good news is there are ways to increase heat resilience through urban design by implementing cooling interventions. And I'll start to talk a little bit about that in a bit. But first, I want to show you Grape Street Elementary. This is sort of a typical built environment profile for most public schools. You have some trees, a little bit of grass. On the whole, though, it's a lot of asphalt and pavement, big open area, play area. And as you can see, it's, buildings and it's mostly asphalt. So we used EnviMet software to model the baseline conditions. And also we plan to do plan interventions in future scenarios. One of the potential limitations of this software, I would just like to say, is that sometimes it overestimates mean radiant temperature by 5 degrees, but it does so in a consistent way. So we get a strong sense of the trend, and then we can actually compare it to actual observations to calibrate the model. So for today, we wanted to present model results for surface temperature, air temperature, mean radiant temperature for 4 times during the day. So 8 a.m., 10 a.m., 12 p.m., 3 p.m., and then kind of compare those 4 locations to give you a better sense of how much of a difference the built environment can make. So we're looking at one area. This is a major roadway next to a metro line. So we look at temperatures here. This is the schoolyard. So we dropped a point in the middle of a schoolyard. This point over here is a shaded sidewalk outside the school. And then this other point is a residential yard with grass cover, fully sun exposed. And this is the results from that. So the land surface temperature and air temperature and mean radiant temperature were modeled for September 4th, 2019, when data was gathered. They follow general diurnal trends, so rising throughout the morning, reaching peak temperature in the afternoons. But first, we'll start to see some differences. But first, I want to just point to air temperature for all 4 of these areas. Notice that they're pretty similar: 26, 26, 26. 10 a.m., 29, 28, 28. There's not a lot of variation. And I highlight this because it just shows why air temperature really isn't a useful indicator when thinking about thermal comfort at the human scale or trying to assess the effectiveness of cool design interventions. I think we all intuitively know that if you're, standing under the shade of a tree or a building, it feels a lot cooler than, say, being out on an open road asphalt, right? Now, when you look at the land surface temperature, follows pretty typical trends too. Asphalt of the schoolyard and the roadway are about the same. That makes sense. Fully sun exposed asphalt gets really hot. The grass is cooler, but not as cool as the shaded area. Even though this is a sidewalk with cement, the fact that it's shaded by the tree in the building makes it cooler. Now, the mean radiant temperature, you see the large fluctuations are really due to shade versus sun exposed, and then secondarily ground cover. Notice that the schoolyard and the roadway metro line consistently have the same temperature. So it's just as hot in that schoolyard as it is, standing on a road next to a metro line. The residential yard with the grass definitely helps. That grass cover lowers the temperatures, but it's still pretty hot because it's sun exposed. Whereas that shaded area, that sidewalk, is the coolest. So really what this just says is just how powerful shade is to pedestrian comfort. It's really all about that shade. So next, I wanted to show you one of the EnviMet outputs. This is just to kind of give you some visual context of what I was talking about. This is mean radiant temperature at 12 p.m. Those dots that I was talking about, again, here's the schoolyard. This is the roadway with the metro line. This is the shaded sidewalk. And then this is the residential yard. As I mentioned, the schoolyard is consistently the same as the road in terms of mean radiant temperature and land surface temperature. The big takeaway I want to emphasize here is that the typical schoolyard built environment as they're currently designed means that it's as hot as walking on a highway right now as it stands. Another takeaway, and this has been talked about in many papers too, is that urban form, or the spatial arrangement of these buildings, has a larger impact on daytime temperatures at the micro scale, human scale, compared to land cover or landscaping. So look at all that shade that's being provided by the buildings. I mean, it's fairly significant, and that really does impact the temperatures. And lastly, what I really want to emphasize is the importance of using mean radiant temperature as the heat indicator. As you saw, just looking at air temperature, it would lead you to conclude that there isn't much of a difference in thermal comfort from the asphalt in the schoolyard to the shaded sidewalk, but we just know that simply isn't true. There's a huge difference. And the strongest predictor of mean radiant temperature is really shade. So moving forward, we need to be doing assessments at the micro scale. We need to be including mean radiant temperature in those assessments. And we can't just think about surface cover alone. We also need to think about shade. So for next steps, we'll be doing some baseline microclimate models of other schools in the Watts neighborhood, as well as the other communities. Then be modeling planned interventions, and then working with stakeholders to figure out future scenarios, like if they could put a shade structure here, or best case scenario, these many trees, this type of shade structure, what would that do? So those will be the next steps. And I just want to acknowledge, again, our collaborators and community stakeholders and our funders. Just really wouldn't be possible to do this project without Watts Rising and Climate Beautiful, and our funders, of course, the Luskin Center for Innovation and the Strategic Growth Council, Climate Change Research Center, and the Sustainable LA Grand Challenge Sandpit. And thank you everyone for listening, and I'm happy to take questions.
Great, thank you so much, Morgan. Can you hear me?
I can hear you, yes.
Okay, perfect. I just got a notification that my audio stopped working, but I'm glad that it's still operational. So you did speak quite a lot about the land surface temperatures, ambient temperatures, and that mean radiant temperatures. Can you speak a little bit further about how that MRT could be better used in research and practice?
Absolutely. So, I guess the big challenge, as I mentioned, the reason why probably this hasn't been incorporated in a lot of studies is because it is difficult to measure. There are some tools out there like Kestrels that can model mean radiant temperature that are a little more affordable. And then there's MARDI, this mobile weather station developed at Arizona State University by Dr. Ariana Medell, that's highly accurate. But what it means is we're probably going to have to invest more in our heat assessments. It's just not a quick, easy, let's do a land surface temperature map using readily available satellite imagery. It is useful. They are useful indicators, but if we really want to think about investing in cooling mitigation strategies, we're going to have to use some equipment and do very hyper-local measurements.
Okay, great. You also spoke a little bit about the importance of building form and kind of the shape and massing of buildings. Could you speak a little bit more about, the layout, the shaping and massing of buildings? And there's conversations about concerns about increasing density and how that might contribute more to, increasing heat severity. So could you speak about that a little bit more too?
Yeah, absolutely. Right. I think there's a lot of time it's like, okay, the more dense we make it, the more impervious cover we might have. But what's interesting is in terms of mean radiant temperature, having higher buildings and closer together provides shade, believe it or not, and it's a lot cooler in what you would say it's like these urban canyons. Makes a huge difference. But I wouldn't say that it's, a panacea. Like as Evan was talking earlier, there's going to be different solutions depending on the context. Like in some instances, maybe having more trees might be a better idea, or cool roofs. But I will say that, having these buildings clustered does actually provide quite a bit of shade. And when we were touring some schools, actually the coolest areas on campus, it wasn't that grass field. It was really, I've noticed, it was in between each of the school buildings. And I found myself, we were talking to the principals, we were like trying to like stand between school buildings in the shade. Those were the coolest areas. So it definitely makes a big difference.
Okay. I have one question from the audience. Have you engaged K through 12 students in your heat measurements? And if not, do you have any ideas of how they might be engaged in this kind of work?
Yeah, that's a great idea. I know that Dr. Kelly Turner's had some other projects around this where she did a cool paint, like a cool wall paint mural at an elementary school, and she was able to engage some kids with the artists about doing some measurements with heat sensor guns and designing the mural. In terms of moving forward, I think it would be great. I think that's a great idea because it's an education part. And it is, I think, quite fun too, the little temperature to get the surface temperatures and stuff. And it's quite easy to set up an air temperature gauge and do thermal cameras. So I like that idea.
Okay.
Yeah.
Another question, I'll condense a few of them, but the idea of what kind of strategies would be appropriate for schools to implement to help cool their schoolyards, and kind of throwing it in there, those schools that do have those artificial turfs that you found to have higher temperatures, how they should consider those investments they've already made.
Yeah, I mean, we're just starting to look into AstroTurf. I'm trying to figure out actually how to model it in the NVMet software to create a heat profile for it. But just from the land surface temperature maps, you could see that it's as hot, if not hotter than asphalt. So I think there should be some consideration on maybe replacing those. But I know there's a lot of trade-offs, right? In really hot areas that are experiencing drought, there's water issues. I think Evan talked a lot about too local contexts and just various trade-offs that you have to think about. Whether you can plant a lot of trees. Like for example, some schools were offered trees for free, but like one of the things that they were concerned about is that in planting trees, you have to create sort of these wells around it, and they worried about like a tripping hazard. Playgrounds typically have rubber matting, and the reason being is to break a fall. That's really important. But what we found is that rubber matting is hotter than asphalt. So now you're like, but so what are the trade-offs there? So I would say like a big one is putting shade sails over playgrounds. Like as much as you can to create shade, and it doesn't just have to be trees, it doesn't have to be like cluster buildings. There's artificial ways to create shade to block that solar radiation is going to make a huge difference.
Okay, great. And to our session operator, if they could bring the other panelists back on, I have a final wrap-up question for everyone. So while they're starting to rejoin us with their cameras and mics, I think we're still missing Mary. Yeah, so I'll get started, and if she's able to join us, we'll have her join too. But for Evan and Morgan, for right now, a thread running through all of the questions, or a thread running through all of the panel presentations that we had was really the need to approach heat planning and research in a much more nuanced way than has been done in the past, and kind of not just using the urban heat island map that is widely available and those land surface temperatures for decision making. So can you speak a little bit more to the importance of these nuances as kind of like your final thought for this panel? Speak more to those important nuances, both for research and for decision making and practice, and kind of as our understanding of the complexity of heat makes it seem more complex than ever, how we can still kind of have some lessons learned from this that decision makers can go out and make some decisions immediately from. So Evan, I'll start with you, and then we'll go to Morgan next.
Sure. So yeah, I mean, it's the biggest thing that we need to absolutely be doing is moving beyond land surface temperature. In fact, in all of the various air temperature models that we've been running in the Urban Climate Lab, we do like to compare those to land surface temperature just to see how well they match up, and the correlation is very low. And in fact, in highly naturally reflective cities like Phoenix, where the natural landscape is actually quite light in color and reflective, you can actually get sometimes the opposite, where the hot spots in the LST map are actually the coolest spots in the air temperature map. And so that can be quite a bit misleading. And so we absolutely need to be moving towards, unfortunately for cities, as Morgan was saying, putting more funding behind actually modeling these kinds of air temperatures, because they can be quite pricey. But we just need that kind of data to really know where to be intervening. Coupling them together with some of these other models like the interior models or even individually experienced temperature using synthetic data sets to get as close as possible to the lived experience is going to be really important. But this is where also I just want to end here with both the active and passive is what we need. We need to be determining how to best be modifying our environment, but also our lived experience as humans, and what kind of resources we have available to have more control over our own thermal exposure.
Great, thank you, Evan. Morgan, you next.
Yes, maybe I agree with everything that Evan just pointed out. Particularly, yeah, we need to go beyond land surface temperature. I think that's, it's pretty clear from these presentations and other work. It is going to cost a little more, for example, to measure mean radiant temperature, but it's critical because when you're thinking about designing cities for people, we're talking about like at a street segment, a pedestrian walking down the street, we're talking about kids in a playground, and those thermal environments, they're scale dependent. They're influenced by, obviously the local weather conditions, but also the urban design and also the thermal properties of those surface and building materials. And so moving forward, as we start to put more funding in cooling mitigation design efforts, we'll need to do more accurate heat assessments to make sure what we do is effective.
Great, thank you so much, Morgan. And Mary, I'll turn it over to you last.
Yeah, sure. I think it's a tough one when I think about the focus of my presentation. A big one was that indoor environment, and there are resources to help people with that, but there's just not enough funding. There's way more people that need help than the money is there to actually assist them with air conditioning and these sorts of things. And so, it's not necessarily the easiest thing for us as researchers to do. We're not always the policy people, but if we want to make a difference there, we have to sort of get involved with policy decisions.
Great, thank you so much. And I would just like to thank Mary, Evan, and Morgan again for their presentations, the questions and answers, and the discussion at the end. Up next for this Adaptation Symposium at 10:45 a.m. There are 4 sessions that you can choose from. And again, as was mentioned earlier, they will all be recorded. So if you want to attend all of them, you'll have the opportunity to watch them all later. And thank you again for joining us. And we look forward to the rest of the symposium. Have a great day.